Okay, let us now look at the exercises. The first one asks us to prove proposition 364. So proposition 364 is the one where it is asserted that the relation of two sets having the same cardinality is an equivalence relation. So three sets x, y and z were chosen. The first assertion asks us to show that, or the first assertion is that x has the same cardinality as x. That means by definition of that relation, we have to show that there is a bijection with x both as domain and range. So we start the solution like this. For any set x, consider the identity map this is the map which does not change any element of x. That is, if you take any element of x and put it as an input in this map, then that same element is given back as output. Since this map is a bijection, we already know this, or in fact you can quickly verify that this is a bijection. This is a bijection in a very trivial way. The bijection x has the same cardinality as x. Okay, then this shows that this relation is reflexive. Every set has the same cardinality as itself. Next, we show that the relation is symmetric. Next, assume that x has the same cardinality as y. Then by definition, there exists a bijection, say f from x to y, whose domain is x and range is y. Okay. By exercise 336, the inverse map, first of all, such a thing exists because f is a bijection, and the other fact is that the inverse itself is a bijection, is also a bijection. So we now have a bijection with domain y and range x. So by definition, y has the same cardinality as x. So that shows that this relation is symmetric, and finally we now show that the relation is transitive. Finally, assume that X has the same cardinality as Y, and Y has the same cardinality as Z. So then we will have two bijections then there exist two bijections, say H1 from X into Y and H2 from Y into Z. By exercise 337, the composition of these two maps is also a bijection from X into Z. Hence, X has the same cardinality as Z. This shows that this relation is transitive. So it's an equivalence relation on the class of all sets. We can think of it in that way. Now there is a small thing that I want to draw your attention to. You see, we sometimes get confused while writing the composition of a mapping. We have already discussed about this when we learned about compositions. However, it sometimes happens, and especially here where we write the argument of a function to the right of the function. For example, here H1 comes after H2. The way we are writing in going from left to right, we will write H2 first and then H1. That's because the function is taking us from X to Y and then from Y to Z, the composition. So you have to be able to apply H1 first. So since we are writing the argument to the right of the function, so H1 appears here and then H2. However, in Herstein's topics in algebra, since he sometimes is writing a functional value like this, where this is the argument and this is the function. So the same composition in Herstein's notation will be just H1 composition H2. There you don't have to think about the order in which the functions appear. They appear in whatever way you see them, that's how they appear, because here this is how we will calculate the value of the composition at a point. So here again we are applying H1 first, and then on the result we are applying H2. Okay, so the next one is exercise 362. Show that a set X has cardinality 0 if and only if X is the empty set. X has cardinality 0 if and only if what is the definition of having a set having cardinality 0? If and only if there exists a bijection between X and this set, that's what X being of cardinality 0 means. Now look at this set. This set is the empty set, since the set, the range of the function f is the empty set the first sentence, this one, is equivalent to the condition X equal to the empty set. Why? Emptiness of this range implies and is implied by this condition. Why? And that why is answered in exercise, or I should write it like this: see exercise 333. There we have seen that such a function where one of the sets is empty, either the domain or the range is empty, is a bijection if and only if the other set is also empty. Okay, so this completes the solution. Then the next one, 363. Let n be a natural number and let f be a function whose domain is this and range is the set of natural numbers. Be a function. Show that there exists a natural number m such that all the functional values are less than or equal to m. For all I lying between 1 and n. And there is the hint we will follow this hint in the solution. Induct on n, apply induction on n, and there is something else also. You may also want to peek at lemma 5114. This is something that comes much later, so we are not going to say anything more about this lemma. So in this exercise we see that we have to prove that thing which we left unproved in the proof of the assertion that the set of natural numbers is infinite. There we used this fact that any such finite sequence of natural numbers has a so-called upper bound without proof. So in this solution we will prove that fact. So that's why this exercise shows that every finite subset of the natural numbers is bounded. We are not saying what bounded means actually, but you can understand what it means. This is a bound beyond which the elements cannot go. In that sense, you can see that the set of any subset of the set of natural numbers is bounded from below by 0, because every natural number is greater than or equal to 0. So let us proceed with the solution. We apply induction on n. When n is equal to 0, the assertion is vacuously true. Why? What is the assertion? The assertion is that this happens. Whatever the value of n is, this happens. But in this case, in the assertion we have n equal to 0. So in this particular case, we can write the assertion slightly differently like this. If I is a natural number such that I lies between 1 and 0, then it implies that f of I does not exceed n for all I lying between, or we don't have to write that. So this is the assertion, and this is an implication where the hypothesis is false. So regardless of the conclusion, the statement is true and it's vacuously true. So that's why we are saying in this case it is vacuously true. This is false because no natural number satisfies both these inequalities simultaneously, and that is the basis for our induction. So we now assume the induction hypothesis. Assume that the assertion is true for some natural number n. Okay, for some n belonging to n. Let f be a function from this set, we now have to consider the assertion in the case where we have n plus 1 in place of n. So we consider a function that looks like this. Let this be a function. Consider the restriction of f to the set consisting of the first n positive natural numbers. That is, we are restricting f to this part of the domain. And in fact, okay, you can understand by the definition of restriction, this is just the function f but with a slightly smaller domain where the point n plus 1 is not there, everything else is same. The formula or the rule for the function is just like f, only the domain is smaller, it's a subset of the domain of f. Now this restriction is a function that looks like this. Where here we have n. So by the induction hypothesis, the functional values for this function, this restriction, will have an upper bound. By the induction hypothesis, there exists a natural number n such that g of I is less than or equal to m for all natural numbers I lying between 1 and n. Okay. Let m prime be the maximum of this n and the value of the function f at the point n plus 1, which by definition is the bigger among these two. That is, if m is greater than or equal to fn plus 1, then this maximum is m, otherwise it is fn plus 1. You understand this. Note that f of I is less than or equal to m, or we can write like this, instead of directly writing f of I as such, f of I is equal to g of I if I is a natural number lying between 1 and n. Okay, because in that portion of the domain f is nothing but g by definition, and from this condition we already have this. Now since m is I want to say that m prime is the bigger one between m and fn plus 1. So in any case, m prime, either m prime is m or this one. In any case, m is less than or equal to m prime for all natural numbers I lying between 1 and n, and additionally fn plus 1, since this is also greater than or equal to fn plus 1, so we have this as well, that is fi is less than or equal to m prime for all I lying between 1 and n plus 1. Now it's clear, it's also clear that the whatever the maximum value may be, it's either this one or this one, so it's a natural number. Since m prime is also a natural number, this completes the induction, because in this case we have found an upper bound which is m prime. And also completes the solution. So the gap that we left in the proof of infinitude of the set of natural numbers has now been filled with this thing being proved. Okay, so next, the fourth one. This is going to be a long one. Proof proposition 3614. Proposition 3614 is the one which is named cardinal arithmetic. So all those subdivisions and all those things we are now going to prove. And we have to now recall one by one what those assertions were. So in the first part, we were given a finite set. In part A, we were given a finite set x, and small x was an object which is not an element of capital X. Then this union is also finite and its cardinality is one more than the cardinality of x. That's what we have to prove. This is not very difficult, but let's go through the solution. Since x is finite, there exists a bijection f from or between I think it's better to write in the next line. Okay, So here what we are doing, since x is finite, it will have some natural number as its cardinality. According to our notation, this is that natural number, and by definition of x having this cardinality, there will be a bijection between this set and x. All these things are coming from definition. Okay, now define a new function g from this set into this union by this formula g of, okay, since x is a special element, so we write g of y. G of y is defined to be equal to, or I can take I also, since our inputs are natural numbers. G of I is defined to be equal to f of I if I lies between 1 and the cardinality of x, and it is defined to be equal to x if I is equal to the cardinality of x plus 1. Is this mapping well defined? That is the first question. You take any element in the domain of this map, say you take an I, that I will either lie between 1 and the cardinality of x, or I will have this particular natural number value. Say I is something here, then by definition g of I is equal to f of I. Since f is a well defined function, so this f of I first of all is an element in x, and hence an element in x union x. And because of well definedness of I, f, the second thing we get is that this f of I for that given I is a unique element in x. So that's why it stays unique in x union x also. If I has this value, then by definition g of I is x, which is in this union and which is unique. We don't have any other thing associated to g of I in this case. Okay, so g is a well defined function. For well definedness, every output must be in the range, and for a given input the output must be unique. Although we won't write all these things, we just simply write clearly g is well defined. Now we can also quickly see that G is a one-to-one mapping or an injective mapping. How is that so? Say you take two elements I and J in the domain of G. Okay, such that their G images are equal. Our aim is to show that I is equal to J. Okay. If it happens that I and J are different in the sense that I lies between 1 and the cardinality of x, however J is this thing, what do we then get from this equality? Then G of I will be equal to f of I and G of J will be equal to x. Now note that f of I by definition is an element in X. However, according to the way we chose this object X, it was initially not in, originally it is not an element of X. So here we get a contradiction. So that means if or in other words, we cannot have a situation like this. So that means if we have Gi equal to Gj, then either both I and j satisfy these inequalities simultaneously, or both of them are equal to this. A similar contradiction appears if you consider j here and I here, which is actually nothing different. We are just considering them in an interchanged manner. So let us now write these things properly. Next, let I and j